Hey, welcome back. Today we're going to build on the ideas we had last time, as we always do, and we're going to look at the root test, which is very similar to the ratio test in the way that the conclusions are kind of made, but it works with a different object. So in this case, we're looking at the limit as n tends to infinity of the nth root of the absolute value of the nth term. Right? So to think about what that might mean, if we look at a series that has the form 1 over n to the n, so this is 1 over 1 to the 1, and then 1 over 2 squared, and then 1 over 3 cubed, and then 1 over 4 to the 4, and then 1 over 5 to the 5, and then 1 over 6, you get the idea, right? And that goes on forever. The power of the root test is that it looks at the limit of the nth root of the nth term. So in this series, the nth term is 1 over n to the power of n. So what's the nth root of that? Well, the nth root, it's positive, so the absolute value is not doing anything here, but the nth root is the nth root of the nth power of n. Or to put another way, this is 1 over n to the power of n raised to the power of 1 over n, and when you distribute that power, you've got n times 1 over n, so this is just 1 over n, right? The nth root of the nth power, well, they cancel out. There are inverse functions. So the nth root of the nth power in this case is just producing this 1 over n term. What does that mean for convergence? Well, if the number that you get in the limit is less than 1, then the series converges absolutely. And so in this case, you can see that this term is going to go to 0. So if it goes to 0, it's definitely less than 1, and therefore this series is convergent. Let me write that out. So what we've just shown is the limit of the nth root of the nth term is going to be just the limit as n goes to infinity of 1 over n, and that's going to be 0. And that's definitely less than 1, and so by the root test, the series converges. In fact, it converges absolutely, because that's what the root test guarantees us. Just like the ratio test, this is a test for absolute convergence. Let's do another example. This next series involves alternating terms. We've got minus 1 to the power of n. That's the alternating. And in the denominator, we've got the inverse tan of n, but that's then raised to the nth power. And so the thing to notice here is that the power of n, right? Everything here is raised to the power of n, and that suggests that the root test might be applicable. The root test is going to be useful to us when things are raised to the nth power. So the nth term here, the general term, is minus 1 to the n over the inverse tan of n, all raised to the nth power. And so what we want to look at in our root test is the nth root of the nth term's absolute value as n goes to infinity. So we're taking a limit of that nth root. And so when we do that in this case, we get the limit as n goes to infinity of this nth root of this complicated beast. But the first thing to notice is the absolute value will get rid of the minus 1, because it doesn't matter. This term's just going to be minus 1 or positive 1, then we take the absolute value, so it's always going to be positive. And inverse tan, as long as the argument is positive, in other words n is positive, inverse tan looks like this. So as long as the x value, and in this case the n value, is bigger than 0, we're going to get a positive number. So this is positive, and so the nth root of 1 is 1 in real numbers, and the nth root of this nth power is just going to leave us with that inverse tan, the inverse tan of n, because the nth root and the nth power are going to undo each other. And so what we're left with is the limit as n goes to infinity of this inverse tan, well, 1 over the inverse tan, and we know that inverse tan asymptotes to pi over 2. So this limit is 1 over pi over 2, which is 2 over pi. And so if it's 2 over pi, we can go back to the root test and say 2 over pi, well, if that's less than 1, this series converges, and if it's bigger than 1, the series diverges. Well, this is 2 over 3 point something, so this is definitely less than 1. So we can say that since this limit of the nth root of the nth term is equal to a number that's less than 1, this original series converges by the root test. Right, that's all we need to show. We need to show that this is less than 1, in which case the root test tells us that our original series converges. So anytime you see things where everything's raised to a power, right, the nth term here can be written as some quantity, all raised to the power of n, and so the nth root is going to undo that power. That's all that's going on. Whenever you see this kind of property, you know the root test is the way to go. Let's do one more example. So our next series almost looks like it's a simple nth power. And notice that this is very similar to a geometric series, right? This is very similar to the geometric series 3/5 to the power of n. That geometric series, we understand how it converges using the geometric series test. We could do a limit comparison test between these two, or perhaps we could do a direct comparison test between these two. Another way to go is to use the nth root test. So just this root test, if we look at the nth root of the nth term, again the absolute value here, where I've dropped the absolute value because for every n bigger than or equal to 1, this is a positive number. And so this is the nth root of, I could write it as 3 to the power of n divided by 5 to the power of n. I could take that out as a common factor. And I'm left with 1 over 3 to the power of n. So that's just a bit of algebraic manipulation. Multiply that in if it's not clear. But this is going to be 3/5 because it's the nth power of the nth root. Let me explicitly write it down. This is the nth root of that nth power multiplied by the nth root of 1 minus 1 over 3 to the n. Just using properties of roots, we can write that. And then this is just 3/5 of now the nth root of 1 minus 1 over 3 to the n. And so that allows us to simplify it a little bit. And if we then take the limit of that simplified quantity, well, as n goes to infinity, this term is going to go to 0. We're going to be left with a 1 here. The nth root of 1 is 1. So this is literally going to go to 3/5 of the nth root of, well, it's just going to become, I'm just going to write it down, it's going to be 3/5 times 1. So this is 3/5. So this is less than 1. And so that series converges by the root test, right? It converges because that limiting quantity of the nth root of the nth term is going to be less than 1. And that's our root test. Now, this one's probably easier to do with, I would do this with a limit comparison test, right? Because I understand that it's very close to this geometric series, so I could use a limit comparison test to decide on the convergence. And the advantage of that is it's often simpler than dealing with these nth roots. So that leads us to the question, when should we use what kind of test? Because we've got a bunch of tests. How should we deploy them? So I'm going to start by outlining these a little bit. The first thing to ask is it one of these series we recognize? Is it a geometric series? If it's a geometric series, then it's of the form r to the power of n, right? Maybe with a constant, n is 0 to infinity. And that converges if the absolute value of r is less than 1. And we can find the exact value of that sum. The only other series we've looked at where we can find the exact value of the sum is the telescoping series. The telescoping series, remember, generally can be written in a form where I'm subtracting terms. So we looked at something like this. So if I had a series that looks something like this, you start writing out the terms and then subtracting things. So this is another example of the kind of series where you can make progress and find the value of the sum, because a lot of the terms cancel. And so the goal here is to look at the nth partial sum. So if you've got a geometric series, find C, find R, determine whether it converges or not, depending on R. If it's a telescoping series, you can expand it out with the nth partial sum and then find whether it converges or not, or find what it converges to, in fact. Only the geometric series and the telescoping series can we actually do that, can we actually find their sum. The P series were 1 over n to the power of p, where n goes from 1 to infinity, and they converge as long as p is bigger than 1. Right? So the way to remember that is that a p series is, well, an example of a p series is the harmonic series, where p equals 1, and you should know the harmonic series diverges. By 1 over n squared converges. So that crossover point is where p is bigger than 1. Right? When p equals 1, it still diverges. P bigger than 1, it converges. So these are our basic kind of tests, and especially the first two. The tests we looked at in the first couple of sections used the geometric series, used the P series to test against, right? We had the comparison test and the limit comparison test. You had to have something to compare with. And those comparisons are the geometric series and the p-series. So you have to know how to work out the convergence of the geometric series and the p-series just by looking at it. You should immediately see things that are close to the geometric series like this. If you look at a series like that, you should say, that's almost the p-series. I wonder if a direct comparison or a limit comparison will help me there. So if it's not one of those two, it might be the telescoping series. But after that, we have to use the other tests we've developed. So let's talk about the order you might do that. So if we have series that have positive terms, and we'll come back to alternating series, but if we have series that have positive terms, then we had two initial tests we could use, the direct comparison test and the limit comparison test. The direct comparison test said, if I want to know about the sum of the AN, and we happen to know about the sum of the BN, then we can compare. And the idea here was we know about the sum of the Bn because this is one of our known series. Typically this will be a geometric series, which I can't spell, or it's going to be a p-series, but it's going to be something we understand. And if you understand it, you know whether it converges or diverges. Now, if these numbers are bigger, this is what the direct comparison test says. It says if these numbers are bigger, if everything's positive, but these numbers are bigger, and this series diverges, then so will that one. But if these numbers are smaller and this one converges, then so will that one. That was our direct comparison test. The limit comparison had the same idea. We're asking questions about the sum of the AN, and we know the sum of the BN because, again, it's geometric or it's p-series. I don't mean we know the values. We know whether it converges or not. That's the key, whether these things converge or not. The limit comparisons looks at the limit as n tends to infinity of a sub n over b sub n. And if that quantity is a positive real number, then these two things will either converge or diverge together. So this is the togetherness theorem, right? It tells us that if this is finite, if this is a finite real number, then those two things either both converge or both diverge, but they do their business in unison, together. There's some more technicalities to that theorem. I encourage you to go back and look at it. But here's our idea, right? If it's one of the simple series, p-series, geometric series, maybe a telescoping series, we have tests. We know how to deal with those series. If it's not one of those, will the direct comparison or the limit comparison help us if it's positive terms? Why would it help us? It will help us because it's similar to a series we do understand. In other words, it's similar to a geometric series or a p-series in the way that this is. The next kind of level of complication are the ratio and root tests, the ones we've just talked about. Now, the ratio test is really good if you have terms that involve exponentials or factorials. So if you see things that involve in the nth term exponential or factorial kind of terms, then this is really good. A sub n is maybe 3 to the n divided by n factorial. Anything that involves factorials, exponentials, maybe other terms as well. Maybe there's an n cubed there as well. It doesn't matter. As long as there's an exponential or a factorial involved, this ratio test will be useful. The root test is generally useful when the nth term can be written as some power of a root, right? Some nth power of a function. This is a really special kind of case. So unless you see something that's really written as the nth term is the nth power, this is a really special test. But the ratio test is very useful as long as you don't have something that's entirely a polynomial. So the ratio test, for example, will show you whether a geometric series converges because it's literally an exponential kind of term. The geometric series has the nth term r to the n. Maybe there's a c there as well. And so this is an exponential with a base r. So the ratio test is really good, and it looks at absolute convergence for any series, right? This works absolute convergence for any series, whereas these tests just look at convergence for positive series. And so there's a difference between where you can use them. And you hopefully will get an idea of this through practice. The ratio test is a good go-to point, But as we're going to see, you're going to need to use the limit comparison and the direct comparison tests often as well. So get a feeling for when they're useful by doing lots of examples, and come talk to me in office hours and I can kind of help you. I haven't mentioned the one series here that we talked about at the very beginning, or the one test we talked about at the very beginning. And that's the integral test. Remember, we said that a series converges along with the corresponding integral. So if a sub n in the series was given by some function and it satisfied a bunch of rules, and again, each of these requires some conditions to be met, then the convergence of a sub n and the convergence of the corresponding integral of f of x, the continuous function, these two, the convergence of them is linked. So this one converges, so does this one. The integral diverges, so does that. But integrals are hard to calculate, right? Integrals tend to be hard. Using the integral test tends to be a lot of work. Remember, we got the test for p series out of the integral test. That's why we started with it. But on a day-to-day basis, it's a lot easier to avoid the integral test if you can. So this is the way I would think through things. Is it one of our simple tests? Is it geometric? Is it p series? Is it one of the series that we understand completely? Is it a telescoping series because we have a trick for those ones? Look at the partial sums. And then if it's a positive series, look at the direct comparison test, the limit comparison test. If you're talking about absolute convergence, you can talk about those two. The integral test is kind of a last resort. And if all else fails, well, if not all else fails, and if you have an alternating series, and remember an alternating series is something where the signs in the series change from term to term, so they generally look something like this, then if you've got an alternating series, remember alternating series looks something like this. So if you've got an alternating series and you can prove certain things about the b's, most importantly, they're all positive and they're decreasing, then the alternating series test will tell you about convergence of that alternating series, but it won't tell you about absolute convergence, because absolute convergence, we would go back here and we maybe look at the ratio test. This ratio test is really our go-to point if we're interested in absolute convergence, but if you've got an alternating series, then the alternating series test is a powerful way to see if it actually converges. But again, when you're doing this, remember to check all the conditions. So by conditions, I mean for the alternating series test, for example, b sub n has to be greater than 0, b sub n have to be decreasing. There's another condition as well. There are conditions on the direct comparison, the limit comparison test that are similar. Make sure you've met those conditions and explain at the beginning of the problem that you have met those conditions. Make sure you tell me what test you're using. It's no good showing you've met these conditions if you never mention the alternating series test. I won't know what you're doing. And then at the end, show that the criteria are met. And the criteria might be, that the limit as n tends to infinity in the ratio test, the criteria you want to show for convergence is that that is less than 1. So you need to show me that that's been met for the series and quote what test you're using. So as you write these up, remember to include all of these pieces because they're important. We're building an argument every time we do these kind of series tests. And that argument is what we need to make a convincing case that the series converges or diverges. Because again, we're doing something amazing. We're adding up an infinite number of things and we're able to decide that the value is going to be a finite value or it's going to go up to infinity or negative infinity, or maybe it'll oscillate. For an alternating series, they often oscillate positive, negative maybe. I hope this kind of outline has given you some idea of how to go about these series, because we've seen a number of things. You really need to have these two basic series completely memorized. You need to know those tests. These are our basic tools, right? Every time we use a comparison test or a limit comparison test, we're using these basic tools. And in fact, So these two series really are our basic tools. Understand them completely. Know how to recognize them, right? Know the form of a geometric series and of a p series. And then you'll be able to use these two tests in a fairly straightforward manner. The ratio test is the most important of the ones we've talked about since, but the root test and the integral test certainly show up. And then for alternating series, it's got its own special rules, and that's the alternating series test. I encourage you to have a look in the textbook in this section. It also has a big list of sort of suggestions for approaching series and using these tests. I hope this has given you some kind of overview, because we're going to now take these tests and return to the land of calculus and actually start applying these ideas to functions soon. Anyway, thanks for tuning in. I hope it's been useful. Come talk to me soon.